Swayam Prabha. Digital India. Educated India.
So, hello everyone, today I will discuss effect of surfaces on the aggregation of protein. So, we will quickly see the last lecture. In the last lecture we discussed what are the different aggregation pathways, one from the native to the intermediate to unfolded to aggregate. Other pathways we discussed from the native protein to directly aggregate, and third pathways we discussed native protein is chemically degraded then converted to the aggregate. Then we discuss aggregation kinetics in the bulk, how the protein molecules aggregate in the bulk due to the external factors. Also we discuss how we can analyze the aggregation kinetics, particularly in the presence of surfaces, where we consider the adsorption followed by the conformational change, then from conformational changes to the nucleation and aggregation. Then also we briefly discussed from the experimental data, particularly the TST fluorescence assay or residual protein concentration, we can determine the rate of aggregation by fitting a sigmoidal curve or a simple exponential expression or a linear slope during the elongation phase. So, today I will discuss particularly the effect of surface on a model protein. So, the model protein will discuss the insulin, and we will see how the surface property, its hydrophobicity, its roughness affects the protein adsorption as well as the aggregation process, then on the change in the secondary structure of the protein, also how it affects the morphology of the aggregate. Then in the latter part of today's lecture, we will try to correlate the surface properties like roughness, hydrophobicity with the aggregation behavior. And in the last, we will quickly discuss what should be the different approaches to inhibit the aggregation of a protein. So, if you recall the last lecture, so we discussed particularly in the presence of surface, the very first step is the adsorption of the protein, and this adsorption lead to the conformational changes. Now, the adsorption depends on the different surface factor, it may be the surface hydrophobicity, it may be the surface roughness, it may be the surface charge, or it is the surface chemistry. So, depending on these factors, there will be the amount of adsorbed protein as well as the secondary structure of the adsorbed layer. So, ultimately after the adsorption there will be some conformational changes, and if that conformational changes promote or support the multilayer adsorption, which we call as a formation of nuclei, and once nuclei is formed, then there will be the formation of aggregates or fibrils at the surface, and after a particular critical length of fibrils, these fibrils are detached in the bulk. So, in that way the aggregation proceeds, particularly in the presence of a surface, and the time required from the adsorption to the formation of nuclei we refer as a lag time. So, in today we will particularly discuss the aggregation of a model protein insulin. So, we have chosen insulin. The insulin is a small protein of 5.8 kilodalton and its size is about 2.5 by 3.5 nanometer. So, insulin contains two chains, let us say this is a chain and this is a B chain. So, A chain length is 21 amino acids and B chain length is 30 amino acids. And these two chains are joined by the two disulfide linkage and there is one more intra disulfide bridge within the A chain. So, typically there are two disulfide linkage between A chain and B chain and one disulfide bridge within the A chain. So, this is a native insulin which is having, you can see the alpha helix, random coil, beta turn and beta sheet. Now, as we discuss, when there will be the formation of aggregates, then the beta sheet or hydrophobic patches of that insulin molecules, they will interact with each other like a formation of the zipper structure, and this zipper structure is rich in the beta sheet and that lead to the aggregation of a protein. Here we are talking about the insulin. Now, we talk about the external factor like a pH, temperature, ionic strength. So, if you talk about in the bulk, if you change the pH lower to 2 and temperature to 60 degree centigrade, then insulin forms the aggregates. So, isoelectric point of insulin is pi of the insulin is about 5.6. So, if you go to the pH 2 means it is pH is less than the pi. So, it will have positive charge. So, depending on this pH, but if you put the pH 7.4, then 7.4 will be greater than pi. At that conditions, insulin is found to be more stable as compared to the pH 2. So, we will discuss how we choose the different surfaces. So, this work has been published in Colloidal surface B. So, we will have taken some glass beads of 1 mm size and their surface was modified to change its wettability or hydrophobicity. So, you can say different functional group was added on the glass bead or glass surface to change its wettability, and after the modification in the glass vial, we added about 200 milligram of the modified bead and 300 ml of the 0.5 mg per ml insulin solution at pH 7.3. Then we incubated it at 37 degree centigrade. So, here temperature is chosen 37 because to avoid aggregation in the bulk, because at 60 degree and pH 2 it aggregates in the solution itself. So, if you keep pH 7.3 and 37, it is reported to be stable for a longer duration. So, here if you are observing any aggregation, so we are ruling out the effect of bulk. So, here the aggregation will arise due to the effect of surface only. So, at 60 rpm 37 degree centigrade it was incubated for different time intervals. After a particular time we have to separate it. So, we have separated the beads and the filtrate the remaining solution. Then you have to wash the bead and then we can dissolve that adsorbed protein using with let us say SDS. any surfactant, then after the desorption we are having the adsorbed insulin in the SDS solution. Also we are having here the filtrate which is having the residual protein as well as the aggregate if formed. So, if you analyze this filtrate we can see whether there is a aggregate and also what is the remaining amount of protein. So, for the aggregate as we discussed we perform the TST fluorescence assay which particularly binds to the aggregates and gives the enhanced fluorescence at excitation and emission wavelength of 450 and 482 nanometer. Then for the residual insulin we can simply perform a colorimetric method like a BCA assay, or sometimes during the aggregation if it is turbid then we can measure its absorbance as well. Similarly, after desorption we can also analyze what is the adsorbed amount on the surface. So, this adsorbed insulin again can be analyzed using the BCA assay, and further these are the surfaces with the adsorbed or the aggregated insulin. So, that morphology can be analyzed using atomic force microscopy. So, these are the different methodology which were used for studying the aggregation behavior of insulin in the presence of different surfaces. So, to avoid the effect of bulk, the experiment was performed at pH of 7.3 and temperature 37 degrees centigrade. Now, what are the different surfaces we have used in this study? So, first is the clean glass surface. So, it is highly hydrophilic, the contact angle is less than 15 degree. Second one was the amine modified surface. So, surface modification part we will be discussing in the module 7 and 8. So, here we form the self assembled monolayers of different functional groups, and depending on that functional group the wettability varies. So, here we choose the amine. So, for amine group the contact angle was 62. So, it is less than 90. So, it is a hydrophilic surface. We also modify with the octyl functional group, its contact angle was 102. So, it is a hydrophobic surface, and also we form different mixed surfaces by mixing the amine plus octyl in different ratio. So, if you mix it, so depending on the, if you remember the Cauchy equation, so its contact angle will be the intermediate between these two values. So, we can design a surface with different wettability by varying the ratio of these two, and the contact angle will be in between 62 and 102. So, these are the different surfaces. So, here you can say this is a monosam of amine, this is monosam of the octyl, and in the mixed SAM we are having both the group. Amine group you can say this is the amine group and this is the, this part is like amine and this part is like octyl group. So, now we have surfaces with a wide range of wettability starting from highly hydrophilic to hydrophilic, then hydrophobic, and the intermediate between the 62 and 102 degree contact angle. So, as I was talking that total energy or total surface energy is the function of the what is the surface energy of A means amine group, O means octyl group. So, Fa is the fraction and the surface what is the fraction of amine group is present and what is the fraction of octyl group is present. So, if you just see here we are increasing the fraction of amine. So, when fraction of amine is 1, the contact angle is 62 degree, when fraction of amine is 0, the contact angle is 102 degree, and intermediate depending on the fraction of Fa and Fo we can calculate using very simple Cauchy equation. So, these dots are the experimental value and the line is the calculated data using the Cauchy equation. So, the data were calculated or you can say the contact angle was calculated using the Cauchy equation. So, we just see the experimental data very well follow the Cauchy equation. So, these are the surfaces hydrophobicity or wettability which are now exposed in the vicinity or in contact with the insulin. Now, there will be different adsorption followed by the aggregation process. So, as I told after a different time intervals the samples were taken out and beads were separated, filtrate was used to analyze the thioflavin T intensity, residual insulin, and the beads were taken for its the morphology of the aggregates as well as the what is the amount of adsorbed protein. So, adsorbed protein was first desorbed, then using the BCASA the adsorbed amount was determined. So, here if you talk about the thioflavin TSA, so initially there is no increase in the TST fluorescence intensity. So, that time we refer as lag phase. So, lag phase considers or lag phase includes adsorption, conformational changes, then multilayer adsorption or formation of nuclei. And once you just consider this point or this point or even this point or this point. So, these points are different lag time. So, what we are seeing and for different surface hydrophobicity we are observing the different lag time, then they are going to the elongation or growth phase, then finally reaching to the plateau. So, lag phase followed by the growth phase, then plateau phase or stationary phase. So, these kinds of aggregation kinetics is we call the nucleation controlled aggregation of a protein or nucleation dependent aggregation. So, what we are seeing here is amine SAM having lag time about let us say 3 hours, octyl is having the lag time about 12 or 13 hours. Then in case of mixed SAM it is having a least amount of lag time. It means the aggregation process starts quickly at the mixed SAM. And also what we did, rather than forming a mixed SAM, we physically mixed equal amount of amine bead and equal amount of octyl bead. And when we physically mixed especially this, then the lag time was different as compared to the if you compare these two mixed SAM and mixed bead. So, what it suggests, although in case of mixed SAM and mixed bead the presence of amine and octyl group will be almost same, but in case of mixed SAM it will have the nano scale morphology. Or it will have the nano structured surfaces due to the formation of mixed SAM. So, it says that apart from the functional group, the surface morphology or the structure of that different functional group on the surface is also affecting the aggregation behavior of the insulin. So, from this TST data we can analyze its kinetic parameters like lag time, rate of aggregation or growth rate. So, one option is we discuss three way. One is you directly fit the sigmoidal curve, Boltzmann equation, or you only consider the elongation phase and fit the an exponential expression, or you take the slope during the growth phase. So, in this we analyze this TST data to calculate the value of lag phase and the rate of aggregation or the growth rate. So, on different surface we observe the different value of lag time. So, amine 3 hour, octyl about 14 hours and mixed 1. So, this is the mixed SAM and this is the mixed bead. So, if you compare, this is the 2 hours and if you compare this is the 5 hours. So, it suggests that the nanoscale morphology is also playing a role here, and also we prepared the different ratio of amine and octyl. So, for those cases also we are having the different lag time. Similarly, we also calculated the growth rate, and growth rate however, you can say it was found to be independent of surface. It looks like the independent of surfaces. So, it says that different surface functional group or different surfaces regulate or control the adsorption behavior, and which ultimately reflected in terms of lag time. And once there is a different lag time, or you can say once the nuclei is formed, then rate of aggregation or growth rate is almost same on, or you can say almost similar on different surfaces. So, followed by that you can analyze what is the change in the secondary structure. So, as we know that there should be formation of beta sheet rich structures. So, this is for native insulin FTIR. So, we analyze using the FTIR. So, this is spectra of the native insulin. So, where we deconvoluted that spectra in, we you just see there are 3 different peaks. So, around 1650 it refers to the alpha helix, then 1630 it refers to the beta sheet, and about 1665 it refers to the beta turn. So, depending on the peak area one can calculate what is the relative fraction or what is the contribution of the alpha helix, beta sheet and beta turn. So, native insulin consisted of 84% alpha helix, 9% beta sheet and 7% of the beta turn. Now, if you just see the secondary structure of the aggregated insulin in presence of different surfaces, in presence of amine SAM, this is in presence of octyl SAM, and this is mixed SAM. So, here if you see clearly, the 1650 peak has disappeared and there is a huge increase in the peak area of the 1630. So, you can say after the aggregation, the alpha helix is completely converted to the beta sheet. We cannot see any alpha helix peak in all three spectra. And again, if you just compare the intensity of, or you can see the relative intensity of the beta sheet and beta turn, it again vary on the different surfaces. So, what it says is, even the secondary structure of the formed aggregate is different in the presence of different surfaces. So, it reflects that there is a role of surface chemistry which is regulating the morphology of the aggregate on different surfaces. But the common thing is, in all the cases the alpha helix peak is disappeared and there is a formation of beta sheet rich structure. So, part of alpha helix is converted to the beta turn and most of the alpha helix is converted to the beta sheet. Now, morphology on the surface, as I told, after the aggregation experiment, the surface morphology can be analyzed using the atomic force microscopy. So, on the glass surface we can say highly hydrophilic, we cannot see any amount of aggregate here. So, it says at highly hydrophilic surface there is a least adsorption. So, that either the formation of aggregation or aggregates is delayed or there is a very little amount of protein in the aggregate. While in case of amine SAM, you can see the elongated structure. So, we just see a elongated structure of the aggregates, and if you go for the octyl or hydrophobic, we can say the globular structure, and if you go in between, in here we are decreasing the amine fraction and adding the octyl fraction. So, this elongation is decreasing and ultimately it is reaching to the globular aggregates, and if you just see the maximum agglomerated structure is observed in case of mixed 1,1 SAM this case. So, what it says, a different surface chemistry is affecting even the morphology of the aggregates. Also we saw the different surface chemistry was also affected the secondary structure of the aggregates, it is also affecting the morphology of the aggregates. So, we observed that elongated structure on amine rich surfaces and globular structure on octyl and octyl rich surfaces. So, once there is a deposition, it means there will be increase in the surface roughness. So, from the FM image we can analyze the average height, or you can say the average roughness is simply the sum of what is the height component, how many number of particles are considered or available in that particular area or the particular site of imaging. So, depending on the what is the height, sum of height divided by n. So, that is the average height. So, of the clean surface, a clean glass surface, the average height was 0.18 nanometer, and due to the formation of different self assembled monolayers, that because of the height of that particular surface modifying agent, we can see there is a increase in the surface roughness. So, it is 0.63 on amine surface, 0.83 on ductile surface, and on mix 1 it is a maximum 1.61. Now, further after the adsorption or after the aggregation, it has increased by many folds on all the surfaces. So, maximum you observe about 8 nanometer on the mixed 1 surface. It has increased from 1.6 to n, but for all other surfaces also, if you see, there is a increase by many folds in the surface roughness, which is also reflecting that there is a adsorption and aggregation of the protein on the surface, and because of the presence of those adsorbed and aggregated protein, the surface roughness has enhanced. So, here we will try to relate the surface roughness with the adsorbed amount. So, typically if we are increasing the surface roughness, means it is expected that we are getting more contact area. So, if there is a more contact area, it is expected there should be the more adsorption site or more adsorption. So, it followed a linear trend. So, which says if you are increasing the roughness, there is a increase in the adsorbed amount of the insulin, and if you remember, the maximum roughness was for mixed 1 SAM, and we got the maximum adsorbed amount about 60 milligram per meter square. So, we can say that adsorbed mass increases with increase in the surface roughness. So, what it is happening is, now we can say, because of the protein adsorption, it triggers the conformational changes, and that conformational changes further leads to the aggregation of that particular protein. So, this is the adsorbed mass of the protein with time. So, you can say on the different symbol indicate the different surfaces. So, here we can see the rate of protein adsorption is different, and the adsorbed amount can be fitted with the exponential function m t is equal to m naught e to the power minus k t, and this k t is the rate of adsorption. So, here we can calculate the rate of adsorption. Now, if you just see what is the adsorbed amount up to 3 hours or so here, which is corresponding to the lag time on these different surfaces. So, here the adsorbed amount is coming close to, let us say, 10 milligram per meter square, and for the insulin, for the monolayer adsorption, its value is about 1 milligram per meter square, and if it is coming to the 10 milligram per meter square. So, it means roughly says that there can be about 10 layers of insulin for the formation of nuclei, or that is the multilayer adsorption, the starting point of the elongation or the growth phase. And during that elongation or growth phase, there is a very rapid rate of adsorption. So, now we can try to relate that adsorption rate with the surface roughness. As we just saw in the last slide, if it increase in the surface roughness, there was increase in the adsorbed amount of the protein, and that is coming because of with increase in the surface roughness there is a increase in the adsorption rate. So, because of the increase in the adsorption rate, the adsorbed amount was maximum where the rate of adsorption was maximum. So, it says that initial surface roughness is affecting the adsorption rate and which is reflected in terms of higher amount of adsorbed protein, and higher amount of adsorbed protein means shorter lag time, or you can say the quick start of aggregation process. So, here based on these observations, so we can assume that this native insulin is a globular protein, it is having a hydrophobic core and the hydrophilic surface. Now, consider the case of highly hydrophilic surface, let us say glass surface. So, there because of highly hydrophilic there is a formation of water layer between the protein and the surface. So, which inhibits the or which interferes with the surface protein interactions. In that case there is a least amount of adsorbed protein, or you can say the aggregation process was delayed for this particular surface. Now, let us consider for the hydrophilic amine surface. So, pKa of amine group is 9.8 and Pi of insulin is 5.6. So, if you are performing the experiment at 7.4, it means this will have positive charge and this will have the negative charge, because at pH above the Pi it will have negative charge, at pH below the pKa it will have the positive charge. So, amine group will have positive charge, insulin is having negatively charge. So, there will be the electrostatic interaction between the amine group and the insulin or the protein, and also because of the amine group can also participate in the hydrogen bonding. So, because of electrostatic and hydrogen bonding on amine surface, we observed the shorter lag time and faster aggregation. Now, let us consider the hydrophobic surface. So, in that case what happens? The hydrophobic interaction will play the lead role here. So, for that first the protein have to reorient, or you can say unfold in such a way that hydrophobic group is coming closer to the hydrophobic surface for hydrophobic interaction. Now, what happens here? In this case the hydrophobic group is there at the surface, but it is surrounded by the hydrophilic groups. So, the formation of nuclei or multilayer adsorption process is delayed. That is why we observed a relatively longer lag time in case of octyl surface. Now, in case of mixed surface where we observe the shortest lag time and faster aggregation. So, here we can say we are having the dual effect of both hydrogen bonding and electrostatic interaction coming from the amine group and hydrophobic interaction coming from the octyl group. So, that is why in case of mixed SAM we observe the dual effect. So, we have got the least value of the lag time and the maximum value of the adsorbed amount in case of mixed 1,1 SAM. So, what it says is the surface which is having the higher affinity for the protein will lead to the or will result in the more adsorbed amount, and more adsorbed amount means higher adsorption rate, and because of the higher adsorption rate it will have the shortest lag time. So, aggregation process will start quickly on that particular surface. So, now after understanding the aggregation behavior in presence of surfaces and in the bulk, what should be the therapeutic approaches. So, let us start with the very first typical kinetics of aggregation. So, this is the lag time, which says there is a native protein is going to the denatured or unfolded, then it is going to the aggregate. So, if you can stop this step from unfolding to the aggregate, but once unfolded protein is present, it is difficult to stop the formation of nuclei. So, you have to work on this step, so that to change the environment in such a way that the unfolding of the protein should be avoided. Second option may be, if you can add a inhibitor here at the U, if you are adding a inhibitor, if you are adding a inhibitor here, then it may further stop the formation of, or you can say this particular intermediate can bind to the inhibitor, so that there should be no binding site available for the monomeric protein to the nuclei, so that formation of aggregates can be avoided. And other step is, if the aggregates are formed, can chemically degrade. If you can chemically degrade or break down it to some smaller molecules or smaller fractions. So, sometimes if it is degraded, it can be secreted out by the body. So, these are the few options available to inhibit the aggregation process. So, different inhibitors are being tested to the specific binding, or you can say the ligand protein interactions, to see how effectively they are able to more stabilize the secondary structure of the protein, or how they are interacting with the intermediates, so that the formation of aggregate or this particular step is avoided. Other step is at the cellular level. At the cellular level, we can just see some mechanism should interfere with the post translational peptide changes before the misfolding or the aggregation. So, if there can be some change at this step, that can also interfere with or stop the misfolding or the aggregation. And the third one is there are some molecular chaperones. So, in the molecular chaperones, what happens? The unfolded proteins comes to the molecular chaperones, and from here they reconvert to the native proteins. So, if body can somehow upregulate the molecular chaperones, so they should be able to take care of the unfolded structure of the protein, and somehow if you can develop a mechanism, because as we know, once the aggregates are formed, they are insoluble, they are toxic, they deposit inside the tissue and cell and associated with various diseases. So, even if the aggregates are formed, can there be a mechanism for the clearance or the secretion or the removal of aggregates. So, one option may be, if you can degrade those, because aggregates are longer in the size, ranging from the, let us say, you can say 100 nanometer to the 1000 nanometer. So, if you can break them down It might happen that cell can automatically secrete it out to avoid the toxic effect of those aggregates. So, these are the few key approaches which are being explored to inhibit the aggregation of proteins. So, I will stop here. So, today we discussed particularly the effect of surfaces towards the aggregation of a model protein which is in the insulin, which is a 5.8 kilodalton protein which has 2 chain A chain and B chain. They are linked with 2 disulfide linkage. There is one more extra disulfide link within the A chain of the insulin molecule, and then that particular protein insulin was interacted with different surfaces. So, different surfaces were prepared by forming self assembled monolayer of the amine group, hydrophilic, octyl group, hydrophobic, and various mixed self assembled monolayers of amine and octyl to form the wide range of batability between the amine and octyl groups. Then they are exposed at different time intervals. Now, the condition for this protein surface interaction was chosen in such a way that there should be no aggregation in the bulk. So, insulin aggregates at pH 2 at 60 degrees centigrade in the bulk. That is why this protein surface interaction was carried out at pH 7.3 and 37 degrees centigrade. So, effect of surfaces was observed. So, after a certain time intervals, the bits were separated to analyze the morphology of aggregates and the amount of adsorbed protein, and the filtrate was used to measure the residual protein as well as the thiophobic intensity change in secondary structure, and we observed that during the aggregation alpha helix is almost converted to the completely converted to the beta sheet and some fraction to the beta turn. Also, we saw the morphology of aggregates depends on the surface chemistry. It means the surface protein interaction decides that what should be the morphology, or you can say the morphology of aggregates, or how protein is unfolded on the surface, that decide what should be the morphology of aggregates. Then we just saw how the surface roughness is affecting the adsorbed proteins. So, we observed that with increase in the surface roughness there was increase in the adsorption rate and the adsorbed amount, and on the surfaces where we observed the maximum adsorbed mass was having the highest adsorption rate, and at that particular surface we noted the least lag time. It means if there is more adsorbed mass, means the lag time will be shorter and aggregation process will start quickly. So, both are the important aspects. What is the conformation of the adsorbed protein as well as what is the adsorbed amount, and these two regulates the adsorption followed by the aggregation behavior. Then we discuss the key approaches, how one can work on inhibiting the aggregation of a protein, because it is associated with various conformational diseases. So, there are we discuss various steps to modify the unfolding process, or from the unfolded to refolding to the native structure, or after the nuclei you block the aggregation process, or once aggregate is there we can devise a aggregate clearance mechanism or degrade those aggregates so that they can be secreted out by the body. So, different inhibitors, molecular chaperones and different ligands are also being explored to see their potential effects towards inhibiting the aggregation of a protein. Thank you.